My name is Denan and I am Product Manager at Instrument Systems in Munich, Germany. In my talk, I will speak about measurement systems for UV radiation. As probably all of you know, the UV radiation covers the range between 10 and 400 nanometer and can be classified according to ISO standard into following parts. UVA between 315 and 400 nanometer with typical applications in UV curing and UV ink printing. UVB, main application in skin treatment, but nowadays the most importance has gained the UVC range between 100 and 280 nanometer because of the applications in water and air disinfection, especially during the coronavirus pandemic. Vacuum UV between 10 and 200 nanometer is technically not so important because it is strongly absorbed by atmospheric oxygen. The newest market report from Yole Development also sees that since 2019 the UVC LED applications have overtaken the application based in the UVA range, especially during the pandemic situation, which accelerated this trend. It is also expected that this trend will continue with more high power and new applications. Water disinfection was the main driving applications for UVC LED, but COVID-19 pandemic has changed the deal, making surface disinfection more interesting than ever. It's still going on. But nevertheless, water applications will benefit from these investigations during the pandemic and start a boom for water applications at 2022-23. Yole Development predicts that market revenue for UVC LEDs will grow up to $2.5 billion in the year 2025. For the measurements in the UV range, you have choice of few instruments. Maybe radiometers are the easiest way to perform UV measurements, but they are limited to very narrow wavelength range, typically just around 1 peak wavelength. Therefore, we recommend the usage of array spectroradiometers, which cover the entire UV range and maybe part of also the visible range between 200 and 830 nanometer. The spectroradiometer should perform the stray light correction, which I will show shortly, and depending which unit do you want to measure, for irradiance measurements, different probes depending on the cosine correction quality can be used, and for the radiant flux measurements, integrating spheres made of polytetrafluoroethylene PTFE material with different sizes can be used. The auxiliary light source for UV and visible range can be, for example, a combination of deuterium and halogen lamp. The monitoring of the whole system and the absolute calibration can be performed using UV LED calibration standards, and the whole system should be traceable to some national labs like PTB in Germany. The big advantage of the use of the array spectrometer is that the CCD array detector inside captures entire spectrum simultaneously. Therefore, very fast measurements down to 4 milliseconds can be performed. Since there are no moving parts in the spectrometer, it is a very robust design even for the usage in the production lines. On the right hand side, we see the geometry of the so-called cross-journey Turner spectrograph. On this way, the optical path length is made as long as possible in a very compact design. The usage of the back-thin CCD array as a detector provides high sensitivity for fast testing, even in the normally less sensitive blue and UV range. Also, the highest dynamic range is enabled. So when we speak about the stray light, we mean that a particular element of the array detector registers radiation from a different spectral region than the designated one. For example, the pixel n in the CCD will gain the most signal, of course, from the certain wavelength lambda n, but also register the signal from other wavelengths, which is the stray light. The stray light correction can be applied using a tunable laser after the method developed by the NIST. So tuning the laser at the entire spectrum from the spectroradiometer, you obtain different excitation wavelengths and different responses, so that after application of such so-called stray light matrix, stray light corrected signal of the array spectroradiometer reaches almost the level of the scanning double monochrometer. Here on the graphic comparison of the UVC LED measurement with stray light and without stray light. With this procedure, the optical dynamics in the UV and the blue region will be increased after the performing stray light correction. Here I try to scheme the creation of such a stray light matrix. As I mentioned, to every pixel in the CCD, a certain wavelength will be assigned. We can put different excitation wavelengths and the response to it from the CCD pixel in such a matrix, tuning the laser to the first wavelength in the spectrum. Of course, the most signal will be collected in the first pixel, but also the rest of all the pixels in the CCD will catch some kind of this stray light. So tuning the laser to the next wavelength, lambda 2, the second pixel will obtain the most of the signal, and the rest is the stray light, which will put again here in the matrix and continue the tuning the laser for all the wavelengths up to lambda n. Along the diagonal of such a matrix, this is the real signal, and if we subtract the real signal out of matrix, the rest signal is so-called stray light matrix. This stray light matrix will be applied on the spectral measurements in order to correct for the stray light which is introduced in the spectrum. This method of stray light correction is technically quite complicated and long-lasting. Therefore, we are working on the method of simplified stray light correction. The basic idea here is to create a generic stray light matrix on the basis of existing full stray light matrices for one spectroradiometer type. Then you need just two fast additional device-specific measurements, for example using an edge-filtered halogen lamp measurement and the laser line measurement, in order to adapt this generic stray light matrix to the individual matrix for this spectroradiometer. The software tool for this automated generation of the device-specific but simplified stray light matrix is an essential tool to simplify the procedure, and of course afterwards verification measurements shall be performed. In the result, only 2% in the UV and 5% in the near-infrared region will provide some signal of remaining uncorrected stray light. As already mentioned, the whole system shall be calibrated. That means the spectroradiometer together with the coupling optics and the optical fiber are one unit, and the whole system is calibrated, the wavelength calibration using the mercury argon line lamp. The spectral calibration is done using the deuterium lamp for the UV and the halogen lamp maybe for the extended visible range. The irradiance probes shown on the left side for the irradiance measurements are already calibrated absolutely using the spectral calibration at a certain distance from the lamp. But for the integrating spheres, for radiant flux, there was no absolute LED standard available up to now. The main limit for the usage of the integrating spheres for flux measurement is the occurrence of the fluorescence within the sphere. This can be proven using measurements of a blue LED, shown here in the graph. So the blue LED measurement shows fluorescence on the right flank. In comparison of the PTFE material with poor quality to the optical quality PTFE material, we see much lower fluorescence of the optically best PTFE material, even less than the barium sulfate, which is actually the limited mainly on the visible range. The major influence on the calculation of the color coordinates, especially for the green, is shown in the table below. So with using the poor PTFE material, the right flank will also cause the increase in the color coordinates due to the weighting with the V lambda faction. So that especially in the green, this is very obvious. But the fluorescence of the integrating sphere can be seen in the entire UV range, using, for example, laser variations in the range between 210 and 316 nanometer. Here, just one example for the pump wavelength at 350 nanometer. We see that the old PTF material with not so good optical quality has much higher fluorescence than the optically best material. And if we look at the fraction of fluorescence for different materials on the right-hand side, for the different pump wavelengths, we see that the optically improved PTFE material has the best performance even in the UVC range. Another influence for the optical performance of integrating sphere is the position of baffles, for example, in the sphere itself. The bed position of the ports and the baffles in front of it, shown on the left-hand side, it is made visible with scanning with a very narrow source or maybe a laser line. And improved design, positioning all ports on one sphere side away from the equator, will improve the accuracy in the radiant flux measurements. The black surface of the sphere on the outer surface is in order to minimize reflections for the usage in the lab, and increase mechanical and temperature stability up to 150 degrees Celsius will make these spheres also applicable in another environments. Prior the measurement using the integrating sphere, it is always recommended to perform the self-absorption correction. In the visible range, it is well-known method, summarized here on the left-hand side graph. But this method can be extended in the UV using as an auxiliary source the combined light source for self-absorption correction. It consists of the deuterium lamp for the UV spectral range and the halogen lamp for the visible range. In order to monitor radiant flux from the spheres over time, and maybe perform absolute calibrations if necessary, we have developed a set of UV LED calibration standards, covering the UVA range with a typical wavelength around 365 nanometer, in UVB around 305 and UVC around 280 nanometer, with typical radiant fluxes around 50-60 milliwatt. The development of UV calibration standard was a challenge because no national labs such as PTB in Germany or NIST in USA could provide radiant flux calibration for the UVB and UVC range so far. Therefore, we have realized traceable calibration to radiant flux using a goniospectroradiometer and a probe calibrated to spectral irradiance in UV. So Instrument Systems is the first company worldwide to provide LED calibration standards for radiant flux in the UVB and UVC range. How does the calibration concept look like? As a detector, an array spectroradiometer with a stray light correction and an irradiance probe was used. But of course, the calibration to irradiance will have a certain amount of measurement uncertainties, which is the biggest contribution in the total budget of measurement uncertainties. The goniometer, in this case the turning luminaire, was used to move this sample and in the whole half space, and the alignment of the goniometer, the measurement of the distance, the scanning procedure of the goniometer itself, they also introduce a certain amount of measurement uncertainties in the budget. The DUT itself, of course, the UV LED standard, is operated with a special control unit, and it will have a measurement uncertainty as well. After the irradiance measurements are performed at each angle tuned with a goniophotometer, the distribution of radiant intensity is calculated using well-known mathematical expression. So this is basically irradiance with the squared distance, and integration over the solid angle omega will finally deliver the value for the radiant flux. The measurement uncertainties for the radiant flux are given in the lower right corner, and even in the UVC range it is 4.5% with the sigma 2 or K2, giving a 95% confidence that the value will be in this range, plus minus 4.5%, which is actually very low, and in the UVA range it is as low as it is in the visible range at 365 nanometer. The result of the goniometric measurements is in the first line the radiant intensity distribution, in this case for the UVA standard. We have traceable values from the PTB, which is in very good agreements for the UVA standard. Since we have no values which are given from national lab for the UVB and UVC range, but we have shown with this method we can also provide the reliable radiant flux measurement for the UVB and UVC range as well. So at the end of my talk I would like to draw some conclusions. I hope I could convince you that the stray light corrected spectroradiometer with various coupling optics is the best suitable measurement system for entire UV range. PTFE integrating sphere should provide low fluorescence, and the self-absorption correction with the deuterium and halogen lamp combination is recommended. UV LED calibration standards can be used for verification and monitoring of irradiance on radiant flux of the system and absolute calibration if necessary. Thank you very much for your attention.